You're building nice bridges. It's a good bridge to the presentation again.
So let's stop here, because if there's something else is winning, I cannot do the bridge. Okay.
All right. We have a crocodile problem again, I think. And now it works. So yeah, I'm going to start with the lowest level of the pyramid, which is the copy section. And our first example is a bolt key, a multi-tool to use for multiple screws and bolts. As you can see, the geometry is pretty small, but the outer dimensions are pretty big. So currently it is made from stainless steel and it's CNC machined. It has a pretty high price, I would say, but since it's a lot of material needs to be removed and it needs machining from all sides, basically, that's where the price comes from. And yeah, we just changed the production technology to binder jetting. The material stayed the same. And yeah, for this, to explain it real quick, so basically you also have a powder bed and a reactive binder. It's printed on top with a print head. After that, the binder gets hardened, and yeah, the greenling then afterwards gets sintered. It's applicable for metal, plastic, and ceramics. And yeah, every technology has some constraints and considerations to do in the design process. So for binder jetting, the size of the print bed, it's rather big. The wall thickness should be minimum 1 millimeter. The complexity can be really high because we use a powder bed and we don't need support structures. But due to the sintering process at the end, the accuracy is only medium because you will still have some deformations during the sinter process. And sometimes you will need also an infiltration afterwards, but the sintering part's always the case that you need that. Yeah, and in the end, for the copy, for the finished part, so the functionality didn't change and we didn't change the design itself. Also, the material stayed the same. We only changed the production technology, and you can see a rather drastic price drop. And I brought the part, which you can see now as soon as we switch the camera. Yeah, so this is the metal part. As you can see, looks pretty close to a milled part. That's one example for the copy level of the pyramid. And then we'll come to the second example, which is on the optimize level of the pyramid. Here we can see a motor holder for electromotor. The current material is an aluminum alloy, and it's currently also CNC machined with a price of 70 euros roughly. And if you start to design for additive manufacturing, you have to ask yourself questions: why is the current part as it is right now? So for example, for this part, why is it made from aluminum? How heavy is the motor which gets attached to it? Are there other influential forces, for example, from the axis of the motor where it's fixed to? And what is the environment the part needs to be in? For example, are there different temperatures? Are there aggressive media like acids or fluids in general? Those are all questions you need to take into account. And you need to really understand the functionality of the part. So for this part, you have two fixing points where it will be fixed to a base plate, and 4 screws which will hold the motor in place. And of course, the hole in the middle as a clearance for the motor axis. And those are the functional features. We need those, we rely on those for our design. And to start from there in the design for additive manufacturing, you just start by connecting those functional parts, because all the rest we don't really need because we add material and don't subtract it. So this is like a minimal connection between all the functional features. And depending on the material, you have to make it a little bit sturdier. And yeah, if you come to that design, for example, you will make a simulation for that. I'm not sure if we can show the video right now. Can you show? No, if you go back in the shared screen, maybe. Maybe we can.
Take a look at the right link.
Yeah. Yeah. Okay. Then just go back to that. Okay, maybe we'll show this afterwards, or at least upload it afterwards on the website. So what you basically do, you mesh the part for FEM, and then you apply the forces, which you can see as blue arrows. One is the weight of the motor, which of course will be a downward force. And the second force is the torque of the motor. Then we also have a temperature, which in this case was around 50 degrees. Then you have constraints. At the end, you have the bolts, which fix the part to the base plate. These are the constraints. And of course, you have to apply the gravity. At the end, you then apply a material so that the software also can simulate the displacement. Yeah, for this part, the deformation at the tip was a little bit too high for the clutch, which will be fixed to the motor. So in this case, we made it a little bit sturdier with 2 additional struts so that the displacement will be lower. Yeah, production technology for this one was powder bed fusion with polymer. So the material chosen was PA12, which is a nylon polymer. And the technology specific for this is then selective laser sintering or multi-jet fusion. Since they are both pretty similar, it more or less doesn't make a difference which you choose. Yeah, that's a short video of the process itself. You can imagine on the right, the black one, that's a roller or a coater. It will push a new layer of powder from the powder reservoir on the build plate. And on the build plate, the laser from the top will melt the polymer and then go down 1 layer height. And the recoater will put a new layer of powder on that. And the laser then again will remelt the powder and fuse it also with a layer below that, so that at the end you have 1 solid part. This technology also has some design constraints. The size is, as you can see, also pretty big with the new machines. The wall thickness is slightly smaller than for the binder jetting. The complexity, since we are still in the powder bed department of additive manufacturing, is also pretty high. And the accuracy, since we don't need support structures, is also pretty high. And because also we use a laser and not like an inkjet technology or for example, the binder you've seen. For the part orientation during the print, it depends a little bit on the forces and the important features you have. So the process itself, it's most accurate in the XY plane, and also in the XY plane, you have the highest strength inside the part. And for this specific parts, we didn't need threads. So, but as Alexander showed you in the beginning, it is possible to include nuts into prints. And it's also possible to include or to insert threads. Maybe I can show it here also. That works. It's just metal threads you can more or less melt into the polymer parts. And that's one way to include threads. Threads can also be printed directly with some of the technologies, but mostly it's for threads bigger than, or at least M6 or bigger. Yes, then there we can see the final result. So the functionality stayed the same, but we changed the material and optimized it in that way. The used technology was selective laser sintering, so powder bed for polymers, and the price decreased for a good amount. Then we have a next example. this part is a rotational axis arm. It's currently made of stainless steel and CNC machined. So again, we ask questions, why is it as it is? So why is it from stainless steel? Where and how much force is applied on it? And are there other influencing forces? What is the environment? And are there some specific tolerances? So to understand the functionality, so in the front, we have a force which is applied. In the middle, the triangular shape is, so that dirt doesn't stay on it, that it falls down left and right. And at the end, we have the keyway for the axis and also for the axis H7 fit. So when we optimize, so most of you would probably do the left one, which is like just putting holes to save on material and to reduce the mass. But as we told in the example before, sometimes it's just useful to only connect the functional parts so that you already have a minimum amount of material. That's what happened on the right side. And since it's so thin, also the dirt will not stay on there. So this one specifically was printed in SLM, which is selective laser melting. Also, the material stayed the same because of the environment this was used in. That's the video of selective laser melting. You can imagine it more or less the same way as the selective laser sintering process, but with one difference. So for selective laser sintering, which is the polymer powder bed technology, you don't need support structures. In this case, everything is always built on a build plate, so it will always be attached to the bottom, and you need support structures. So afterwards, during the post-processing, you need to remove those support structures and you need to cut your build parts from the build platform. And also, in this example, some post-machining can be done, for example, cutting threads or do a sandblasting for the surface. Okay, so SLM also has some constraints, as you can see here. The size of the maximum build dimensions is a little bit smaller than the previous ones. That's also due to the temperatures and the power of the laser. The minimum wall thickness is around 1 millimeter, which is advised. You can go lower, but at lower wall thicknesses, of course, the process might not be that reliable. The complexity is between medium and high because we need support structures, so not everything can be built like with a freeform. The accuracy is pretty high since we are using a laser. And again, here, the orientation of the build job, it's the strongest and most accurate in the X and Y plane. And for this specific part, we didn't need any threads. So again, threads can be printed directly or machined afterwards. So as a result, since we have very thin struts between the functional parts, the cleanability is improved, which is the optimization in form. Material stayed the same, and we changed the technology to selective laser melting, which is the powder bed technology for metal. Then we come to the third level of the pyramid, which is the integration. For this, we use as an example a tool holder. This is a tool holder for a sheet metal bending machine. So basically it holds the tool for the bending. As you can see on the right side, it's an assembly with a lot of parts. The function, it's a tool holder. It's currently made from steel and it is CNC machined. And since it's an assembly, we have a tolerance buildup. So each single part had a very tight tolerance so that the last tolerance for the tool is okay-ish for the manufacturer. And we need to ask some questions again. For example, what are the forces and weights influencing the part? What is the working environment? And which tolerances and accuracies do we need? Again, we need to understand the functionality of the part. For this part, we have the fixation points for the piston and the axis. You can see on the left picture. And in the middle, we have a accurate surface for an end stop for the machine. And on the bottom, we have the mounting plate for the variable inserts. As you can see here on the left, the tools are fixed to that plate. Yeah, for this, this might be a little bit tricky now without the video. But as you can maybe see where the small light blue dots are, those are the functional parts, and you define them as non-design spaces. So the material there will stay and the software will not remove it. And the big blue part is the design space. So the software is allowed to change the distribution of material within those spaces. You have to define those spaces according to the machine and the interference with other parts in the machine. So you always have to check where you have room for that part, or is there anything that might interfere with that part? This is the second video, which shows the iteration of the software. So you will go from that bulky part on the left to a smaller organic shaped form, which will I show now. So this was the final result of the iterations of the software. Yeah, as you can see, it saves a lot of material. It's a monolithic part, so you only have one part. So yeah, the software also gives an analysis on the stresses and the displacement of the part. And if you change a few settings for the strut creation, you will get different results, which might be stiffer, but also more material, so a little bit more expensive. And the software now, so you put in a material and a target stress, and depending on the target stress, the software will calculate where to add material or where to leave material and where to get rid of it. So this was the final part. The chosen technology for this was also, again, selective laser melting, so powder bed fusion for metal. The material was stainless steel, and I also can show you the part in the small camera. This was, more or less, we'll soon get to it. This was printed in PA12, so it was only like a visualization prototype. But as you can see, you have those organic smooth shapes. Yep. Then we can go back to the presentation. Are we still in there? And when you print the part, here you can also see a prototype. You can also do a quality control, so you can 3D scan your shapes, because it's a little bit hard to measure those parts. So 3D scanning helps with that. And you can compare your printed as-is part with a CAD model, for example, to see if it's still in line. Yeah, this is the finished part made from steel. It looks a little bit different, because this is also post-machined, and sometimes you have some additions to make. This is the printed part and the original part compared. So you can see on the left part, you have the assembly, which also takes time to assemble and have a lot of different parts. And on the right side, you will have the monolithic part. Also, you can see it mounted to the machine. And as a result, the functionality stayed the same. Also, the material, we changed the technology. And the price also for this part stayed the same. But since we now have only one part, we avoided the tight tolerances during the machining, and we don't need to assemble it anymore. And the resulting part was also a lot lighter. So the customer could use a smaller piston. So in the end, even though the part didn't create a cost advantage for the part itself, for the whole assembly and for the whole machine, there was a cost advantage, which can also be an advantage of using additive manufacturing. Okay, then we come to the top of the pyramid, which is the innovate part. we innovated that part on the right, which I will present now. So that part is a bottle gripper for transporting bottles. It's currently made of stainless steel. The complexity is medium-high, but it has an assembly of several parts, and that resulted in a long assembly time. And also there's the problem that it's difficult to clean on the top surface because it handles already filled bottles at some time, and those spilled on it. And also if you clean it with a liquid, also some of that cleaning liquid would stay on top of that part. So again, we have to understand the functionality. In the end, at the back, there it is mounted to the machine, and in the front you have a spring mechanism with two grippers where the bottle neck will go into and removed out of. And for that you need a certain amount of force, and also the bottle weight at that point will be on that gripper during the transportation. So we did a few iterations and redesigns and finally came up with that design. We did some analysis on that regarding stress and displacement, also for the spring mechanism, as you can see here. So we removed the regular spring and made some spring leaves, which are better for printing, as you don't have to have such a flexibility. And there you can see the final part and the previous part, the original part. And it's quite comparable, but also, you can see the difference between the spring mechanisms. There we have the video of it producing. We don't have the video, so I will show you the finished part or printed part in the small camera. So this is the part. You can still see the supports from printing, which is characteristic for selective laser melting. And I'm not sure if it's visible, but the springs have some kind of elasticity. It's not visible that good. But that's the finished part. And of course, also for this part, we can do a 3D scanning for quality control to compare to the CAD model. And in the result, also the top shape is, as you can see in the picture, it was a post machine. It was glass bead blasted, so it's pretty smooth, and also has this downward shape. So we have improved cleanability since we only have one surface, and also the liquids will come off. And we integrated the spring mechanism. The material still is stainless steel because of the liquids. The technology used was, as I mentioned earlier, selective laser melting, and in this case it was post-machined with a glass bead blasting to a roughness of roughly 0.8 microns surface roughness. It was printed in single parts, so it means assembly time reduction. And now it's ready to design for mass customization and mass production because it's an optimized design for printing, and it's also can be adjusted or customized pretty fast for different bottleneck sizes.
Maybe before we go on to the next one, to emphasize again, can you go back? Having a part like this on a critical in a critical area of the machine, 3D printing on its own is never enough. So you always need post-processing, you always need machining for the critical tolerances, but you also need to adjust your design to optimize the design for the production itself. So it's not a magic machine, it's not a black box you put in a design and your design comes out exactly the same. You really need to take into account the process of the printing itself because it works with a lot of heat, it can have displacement, and you need to take that into account for your design to be reliable. I wanted to emphasize on that with this part.
Then I will hand over back to Alexandra, and she will present the next part of the presentation.